Scientists in Taiwan are nervous, very nervous, because what is happening right now in the Pacific is not following the rules. Typhoon Fong Wong has just done something meteorologists say should not be possible. It is intensifying over land. Not weakening, not stalling, growing stronger. And 23 million residents across Taiwan are directly in its path. This is not speculation. This is not a worst-case scenario buried in some research paper. This is happening right now. And the data coming from weather stations across the island is forcing experts to rewrite what they thought they knew about tropical cyclones. Taiwan sits in one of the most typhoon-prone regions on Earth. The island records an average of 3 to 4 direct hits every year. The infrastructure is built for this. The population knows the drill. Evacuation routes are mapped. Building codes are strict. Taiwan has spent decades preparing for these storms. But Fong Wong is different. And that difference has officials making emergency calls at 3 in the morning. The system first appeared on satellite imagery on November 8, 2025, as a tropical disturbance roughly 800 kilometers east of Luzon in the Philippines. Within 36 hours, it had organized into a tropical storm. Within 72 hours, it reached typhoon status with sustained winds of 120 kilometers per hour. Standard progression. Textbook development. Nothing unusual. Yet. But on November 11th at 2:17 in the afternoon local time, something changed. Fong Wong's eye, which had been clearly defined on radar, suddenly collapsed. Wind speeds dropped to 95 kilometers per hour. The Central Weather Bureau in Taipei issued updated forecasts showing the storm weakening as it approached Taiwan's eastern coast. Residents in Hualien and Taitung were told to expect heavy rain and moderate winds, but not catastrophic conditions. Emergency shelters were prepared for roughly 15,000 people, standard protocol for a weakening system. Then Fong Wong made landfall near Taitung City at 11:43 p.m. on November 11th, and that is when the models broke. Within 2 hours of moving inland over the mountainous terrain of Taiwan's Central Mountain Range, where typhoons are supposed to die, Fong Wong's central pressure dropped 12 millibars. Its wind speed increased from 95 kilometers per hour to 165 kilometers per hour. Over land, over mountains, in the middle of the night. Dr. Chen Wei-ling, a meteorologist with 28 years of experience at the Central Weather Bureau, was on duty that night. She said she checked the data 3 times. She said she thought the instruments were malfunctioning. Tropical cyclones derive their energy from warm ocean water. Once they cross land, they are cut off from that energy source. They weaken. They always weaken. This is fundamental meteorology. But our ground stations were all reporting the same thing, she said. Fong Wong was intensifying. By 3:09 a.m. on November 12th, the typhoon's sustained winds had reached 185 kilometers per hour. It had regained. The storm reached super typhoon status while over land. The eye reorganized over Nantou County, roughly 50 kilometers from the coast, with a diameter of just 15 kilometers. It was an extremely compact and efficient structure. Rainfall rates across central Taiwan exceeded 95 millimeters per hour. Rivers that should have been receding were rising. Mayor Lin Hua-yin of Puli Township was woken by emergency services at 3:27 a.m. She recalled that emergency responders told her the entire town needed to evacuate immediately. She said they had already evacuated vulnerable populations the day before, but she was told everyone needed to leave now. The forecast had changed. The storm was not weakening, it was getting worse. Puli Township sits in a valley surrounded by mountains. The town's population was 82,000. The town has weathered dozens of typhoons, but at 4:15 a.m., with rain hammering the streets and wind strong enough to flip vehicles, evacuation buses began moving through neighborhoods, loudspeakers blaring instructions in Mandarin and Taiwanese Hokkien. By dawn, more than 60,000 residents had been relocated to shelters in Taichung City to the west. The evacuation likely saved lives. Between 6 a.m. and 9 a.m. on November 12th, Puli recorded sustained winds of 170 kilometers per hour, with gusts reaching 210 kilometers per hour. 47 buildings suffered major structural damage. 312 homes lost roofs. The May River, which runs through the town center, rose 4.2 meters above flood stage, submerging the entire commercial district. Damage estimates for Puli alone exceed 2.8 billion new Taiwan dollars, which is roughly 85 million euros. But here is what has scientists truly alarmed. This is not the first time this year that a typhoon has behaved this way near Taiwan. In July 2025, Typhoon Gami unexpectedly intensified just before making landfall near Kaohsiung, producing rainfall totals that exceeded 810 millimeters in 24 hours in some mountain areas. In September, Typhoon Krathon stalled over southwestern Taiwan for 36 hours, dumping unprecedented amounts of rain and triggering landslides that killed 11 people. And now, Fong Wong has intensified over land, something that seems to violate basic atmospheric physics as meteorologists understand it. Dr. James Cheng, a climate scientist at National Taiwan University, has been analyzing the data from all three storms. At a press conference on November 13th, he said they were seeing patterns that did not match the models. He explained that tropical cyclones need moisture and heat from warm ocean water. When they move over land, they are supposed to weaken because they lose that fuel source. But something is providing energy to these systems even after landfall. We do not know what. One hypothesis involves the unprecedented ocean heat content in the Western Pacific this year. Sea surface temperatures from June through October 2025 have been 1.8 to 2.4 degrees Celsius above the 1991 to 2020 average. That is not just warm, that is record-breaking. And it is not just surface warmth. Measurements show that heat extends down to depths of 150 meters or more. When a typhoon crosses water that warm and that deep, it absorbs enormous amounts of energy very quickly. But that does not explain the intensification over land. Unless, and this is where the science gets speculative, the mountains themselves are playing a role. Taiwan's central mountain range includes more than 260 peaks above 3,000 meters. When moisture-laden air from a typhoon is forced up and over these mountains, it cools, condenses, and releases latent heat. That heat release can, in theory, provide energy to the storm. But the amount of energy needed to intensify a typhoon is massive. The mountains would need to be producing the equivalent of warm ocean water, and meteorologists have never observed that happening. Until now. There is another troubling element to Fong Wong's behavior: its track. Most typhoons that affect Taiwan approach from the east or southeast, cross the island, and exit into the Taiwan Strait, where they rapidly weaken. Fong Wong took a different path. After making landfall near Taitung, it moved northwest across the central mountain range, then turned almost due north, paralleling the western coast. It remained over land for nearly 18 hours. During that time, it maintained typhoon-strength winds and produced catastrophic rainfall across 7 counties. Changhua County, home to 1,260,000 people, recorded 723 millimeters of rain between November 12th and November 13th. That is more than the county typically receives in 3 months. The Dadu River overflowed its banks, flooding agricultural land that produces rice, vegetables, and fruit for export markets. Economic losses in agriculture alone are estimated at 4.7 billion new Taiwan dollars. Thousands of greenhouses were destroyed. Entire orchards of guava and wax apple trees were uprooted. Captain Huang Jianfu, who commands a Coast Guard station near Lukang, described what he saw. On the morning of November 13th, Captain Huang recalled, the ocean looked wrong. The waves were huge, but they were not moving in the normal pattern. Usually you can see the swell direction, waves coming in from a consistent angle. But these were chaotic, crossing each other. Some were coming from the north, some from the west. It looked like the ocean could not decide which way to move. I have been stationed here for 19 years. I have never seen the water behave like that. What Captain Huang was describing might be the result of multiple weather systems interacting in ways that are not fully understood. At the same time Fong Wong was battering Taiwan, a separate low-pressure system was developing in the South China Sea. The two systems appeared to be exchanging energy through upper-level atmospheric circulation patterns. Meteorologists call this the Fujiwara effect when two cyclones orbit each other, but this was different. Fong Wong and the southern system were not orbiting. They were connected by a river of moisture in the atmosphere, an atmospheric river that stretched more than 2,000 kilometers. Satellite imagery from November 12th shows this moisture corridor clearly. It is pulling water vapor from the equatorial Pacific, channeling it northward through the Philippines and feeding it directly into Fong Wong, even as the typhoon sits over central Taiwan. In effect, the storm is still connected to its fuel source, even though it is over land. The mountains are not providing the energy. The atmospheric river is. Dr. Liu Meihua, who studies atmospheric rivers at Academia Sinica, is cautiously calling this a breakthrough in understanding. She says, if this mechanism is real, if atmospheric rivers can sustain tropical cyclones over land by continuously supplying moisture, then we need to completely revise our forecasting models. It means a typhoon making landfall in Taiwan could potentially maintain its strength for days if conditions align properly. That changes everything about how we prepare. But here is the problem. The models cannot predict when these atmospheric rivers will form. They appear in forecast simulations sometimes, but not consistently. And even when they do appear in models, the models underestimate their intensity. On November 10th, just 36 hours before Fong Wong made landfall, no major forecasting model showed an atmospheric river developing. By November 11th, some models hinted at enhanced moisture transport, but none predicted the scale of what actually occurred. This forecasting gap has real consequences. Maritz Cruz, a nurse working at Puli Christian Hospital, was caught in the rapid evacuation on the morning of November 12th. She recalled that they were told they had maybe 90 minutes to move 47 patients to safety. Some were in intensive care and some were on ventilators. They had to make decisions about who could be moved and how. It was chaos. If they had known 24 hours earlier that the storm would intensify like this, they could have evacuated in an organized way. But they did not know. Nobody knew. The hospital managed to evacuate all patients successfully, but the building itself suffered severe damage. Water infiltrated the second and third floors through compromised windows. Medical equipment worth 180 million new Taiwan dollars was destroyed. The hospital remains closed as of November 14th, forcing residents of Puli to travel to Taichung for medical care. That is a journey that now takes 2 hours because multiple roads and bridges were damaged by flooding. Taiwan's National Science and Technology Center for Disaster Reduction has been conducting a comprehensive review of the island's typhoon monitoring infrastructure. The network includes 1,247 weather stations, 389 tide gauges, 89 Doppler radar installations, and real-time data feeds from 4 geostationary satellites. It is one of the most sophisticated meteorological monitoring systems in the world, and it failed to predict what Fong Wong would do. Part of the problem is computational. Weather models divide the atmosphere into a 3-dimensional grid and calculate conditions at each grid point. The finer the grid, the more accurate the model, but also the more computing power required. Taiwan's Central Weather Bureau runs models with a horizontal resolution of 2 kilometers, which is excellent. But even at that resolution, complex mountain terrain and small-scale atmospheric features can slip through. The atmospheric river that fed Fong Wong was only about 400 kilometers wide in places. In model terms, that is narrow and easy to misrepresent. There is also a data problem. While Taiwan's domestic monitoring network is extensive, it relies on data from surrounding regions, particularly ocean buoy data from the Philippine Sea and the East China Sea. Many of those buoys failed or went offline during Fong Wong's approach. Some were damaged by the storm itself. Others experienced communication failures. At one point during the night of November 11th, data from 23 ocean buoys was unavailable. That left a gap in coverage roughly the size of Taiwan itself. Forecasters were partially blind precisely when they needed the most information. Budget constraints are making this worse. Taiwan's meteorological monitoring budget has remained essentially flat since 2019, while the cost of maintaining aging equipment has increased. 17 radar installations are operating beyond their designed lifespan. Satellite data subscriptions are expensive, personnel costs are rising. The result is a system that's still functional, but increasingly stretched, and the storms are getting harder to predict. The Western Pacific is warming faster than almost any other ocean region. That warmth is extending the typhoon season, increasing storm intensity, and altering traditional storm tracks. Taiwan has been hit by major typhoons outside the traditional June to October season 4 times in the past 3 years. Fong Wong, arriving in mid-November, is part of that trend. Dr. Wu Qianming, director of the Taiwan Typhoon and Flood Research Institute, is blunt in his assessment. He says our models are breaking. Not because they are poorly designed, but because the climate system is changing faster than we can update our understanding. We built these models on 50 years of data that assume certain constants, ocean temperature ranges, atmospheric moisture levels, seasonal patterns. Those constants no longer hold. We're forecasting in a new climate with old tools. The economic toll of Fong Wong continues to mount. As of November 14th, damage estimates exceed 68 billion new Taiwan dollars, roughly 2 billion euros. That includes infrastructure damage, agricultural losses, business interruption, and emergency response costs. More than 340,000 homes lost power at the storm's peak. Some rural communities in Nantou and Hualien counties remain without electricity. Restoring service requires replacing downed transmission lines across mountainous terrain, a process that takes weeks. 1,500 landslides have been identified through aerial surveys. Some are small, affecting only hillside roads. Others are massive, involving millions of cubic meters of soil and rock. A landslide in Renai Township buried 400 meters of Provincial Highway 14, the main road connecting mountain communities to the lowlands. Engineers estimate it will take 6 months to clear and rebuild that section. Until then, residents must use a narrow detour that adds 90 minutes to the journey. But beyond the immediate damage, Fong Wong has exposed a deeper vulnerability. Taiwan's assumptions about typhoon behavior are no longer reliable. For decades, the island has prepared for storms based on historical patterns. Levees are built to handle the worst flooding on record plus a safety margin. Buildings are designed to withstand wind speeds seen in past super typhoons. Evacuation plans are based on expected storm tracks and intensification rates. Fong Wong violated those expectations. It intensified when it should have weakened. It maintained power when it should have dissipated. And that raises an uncomfortable question. What else don't we know? If atmospheric rivers can sustain typhoons over land, what other atmospheric processes might be changing in ways we haven't recognized? Are there other feedback loops, other energy sources, other mechanisms that could make storms behave in unexpected ways? The 2025 typhoon season in the Western Pacific has been extraordinary. Fong Wong is the 23rd named storm of the year. Typically, the region sees 25 to 30 named storms annually, so the total count is not unusual. But the intensity is. 9 storms have reached super typhoon status compared to a long-term average of 6. 4 have undergone rapid intensification, defined as wind speed increases of at least 55 kilometers per hour in 24 hours. And they're not just intensifying, they're behaving erratically. Krathon stalled for 36 hours. Gami's rainfall total shattered records. Fong Wong intensified over land. Each storm has done something that models said was unlikely or impossible. It's as if the rulebook is being rewritten in real time. Scientists are scrambling to understand why. One possibility is simply that this is natural variability, an unusual year in a chaotic system. Typhoons are inherently unpredictable. Small changes in ocean temperature, atmospheric moisture, or wind shear can produce large changes in storm behavior. Maybe 2025 is just an outlier, a statistical anomaly, but there's another possibility that's harder to dismiss. The Western Pacific climate system has crossed a threshold. Ocean heat content is so high, atmospheric moisture levels are so elevated that storms can now tap into energy sources that weren't previously available. The atmospheric rivers feeding systems like Fong Wong might be more common, more intense, more persistent than they were a decade ago. If that's true, then 2025 isn't an outlier. It's a preview. Taiwan will recover from Fong Wong. Roads will be rebuilt, power will be restored, damaged homes will be repaired. But the questions raised by this storm aren't going away. While engineers are clearing landslides and fixing transmission lines, meteorologists are watching long-range forecasts for the rest of November and early December. Those forecasts show conditions in the Western Pacific that remain conducive to typhoon development. The ocean is still warm. Atmospheric moisture levels remain elevated. And the same large-scale patterns that allowed Fong Wong to behave so unusually are still in place. It is not impossible that another system could develop and follow a similar track. It is not impossible that Taiwan could face another major typhoon before the year ends. And if that happens, if another storm intensifies over land, if another atmospheric river forms, if the models fail again, the questions will become more urgent, not just for Taiwan, but for every coastal region in the Western Pacific. Because what is happening here is not isolated. The Philippines, Japan, South Korea, and Eastern China are all vulnerable to the same atmospheric conditions. If typhoons can behave in ways that violate our understanding, if forecasting models are no longer reliable, then millions of people are at greater risk than anyone realized. This is not about whether another storm will come. In the Western Pacific, there is always another storm. This is about whether we can predict what that storm will do. And right now, the honest answer is, we are not sure.